Okay, I do put the videos on YouTube, but I'm seeing myself in a large picture, so I apologize for that. So I'm going to minimize my picture. So when you guys come to the YouTube, if you want to check the slides, I will when I post it, I will send a link to you guys. If it's necessary, you want to go to the class videos and then try to check back what I said. Okay, but in the meantime, it's you guys at home, so you don't actually want to hear me all the time. So I don't know how you guys do it, but I will actually just put up. I just just pull out some papers and actually trying to write the same way I write it to give you a sense of what the kind of line by line derivation would be. And in the meantime, that will keep you guys awake, I think. Okay, so this time we talk about transformation. And I said it's, hey, when you do like the transformations on the discrete random variable, it's really nothing but counting. Next time we talk about Poisson case right here. And then the example would be it's, okay, let me take that out. And then 3 would be it's, if xi is x power Poisson, then I do my transformation. My new random variable is y equals x squared. Okay, then what is distribution of y then, right? Not especially y25. Okay, so y25, then y25 right here, then y25 nothing but x equals to 5. Okay, because y equals x squared. Of course, I emphasize this time it's what happened to x equals to minus 5, right? So x equals to minus 5, the probability is 0 because Poisson counts x never negative. Okay, so then you do know probability of x equals to 5. You pull out your distribution charts and then plug in the x into the PDF of Poisson it. Okay, good. So then what if you do have more complicated transformation than this guy right here? I can certainly do, although I don't know what the real application would be, but say if I have y as a new random variable equals x squared minus 7x plus 12. In that complicated transformation, something like that way, then what is the distribution of y then? Right? Say, what if y equals to 0 right here? Okay, so if y is 0, okay, really nothing but solving for what? This equation right here, right? This equation right here. So, well, you guys get a high school degree, so you know how to do it, right? This guy not equals by nothing as this, right? And then equals 0. And then, of course, x could be either 3 or 4. Okay, so then you guys having probability class already. When I say x equals 3 or 4, what does the or means? Or means in probability means plus, right? I can calculating probability x equals 3 or x equals 4 right here. And then it's nothing but again is, right, trying to calculate probability of x equals 3. And then you do know x following Poisson lambda. And then by the distribution table, you will see Poisson's PDF is this. It's what? X factorial lambda x e minus lambda. And then again, it's probability of x equals 3, nothing but plugging where the x should be. That's it. Okay, I don't give you lambda, so there's no way for you to do exactly the probability. But in this class, I don't have much of a numerical results for you. Okay, this one is the results I usually get. Okay, something as a function of lambda is good enough. Good. Similarly, if you're talking about its probability of x equals to 4, nothing but put in where the x should be. That's it. Okay. So that means, well, if I want to write it more mathematically, it's really something like you finding that space of samples x right there, which satisfy this equation, right? Satisfy right here. Okay, that's how we denote that. If I want to describing a collection of samples, then be written that way, then this guy right here would be the conditions just given to. Okay, so right here is this line right here is something as well, probability equal less where AY may be an empty set. That's exactly really going back to read here. Okay, in this case, I do have probability Y equals 10. Okay, but and then it equals what? X equals to something, say negative 10, square root 10, not negative 10, square root 10, right? But this guy right here is not actually in original sample space. So this guy is 0. So that means this set right here is an empty set. And then you should know that it's whenever you put probability on an empty set, what the value is? Nothing but 0. Okay, so life in the discrete distribution is really easy, but life in continuous random variables is not. But and then unfortunately, the majority we are going to deal with in the future is about continuous random variable. That's likely as a discrete random variable is. Okay, good. So if we really want to deal with the continuous random variable, then what kind of skill we need to have to solving for distribution then? Okay, number one thing you need to pay attention to is you cannot do enumeration anymore because continuous variable have theoretically have infinite numbers, right? It's not like a discrete random variable. You have like countable numbers, 0, 1, 2, 3, countable. But in the continuous random variables, there are so many values, infinite values in my domain. So you cannot just do enumeration. Okay, so there are two things you want to try. At least in my class, these two things will never go away. Or saying that there's no third options for you to do. Number one, CDF. Number two, Jacobian. Okay. First one, how do I using CDF to derive distribution of a new random variable then? It should be straightforward, right? Which means it's if I'm asking you to derive the distribution of some random variable, the number one thing you would think about is, could I derive CDF? If I can derive the CDF of that new random variables, then you win, right? You finish, right? So when I say derive distribution, I did not say anything about do you need to deriving CDF or PDF. When I say derive distribution of some random variable, you could give me either CDF or PDF. It doesn't matter because they are unique. Okay, so it's not going to be have a CDF point to one distribution, but PDF point to another. Okay, it won't happen in statistics, unless it won't happen in our common distributions. Okay, so that means when I derive CDF, that could also give me a PDF by doing first derivative, okay, or by differentiation. Good. So if you understand that, then a lot of things in my class is just nothing but using definition. Okay, so which means, okay, I want to write CDF. Then the first one you want to write down is what? Definition of CDF. Okay, so definition of CDF is this, right? So I got random variable y, right? CDF is nothing but probability of y smaller than little y. Okay, so then I think in my class or in other class and every class in statistics, capital letter right here is usually what? Random variable. Okay, little case right here is fixed value or constant. Okay, so if you haven't have that habits, you need to try your best. Keep telling yourself, capital letter means random variable. Little case means it's fixed value. It's argument, something like that. Okay, it's not random. Okay, good. So then, because I said, hey, if x follow exponential lambda, right now let's new random variable y through that transformation equals x squared. Okay, so because y smaller than y right here, and then y, sorry about that, and then y right here, let me write something right, equals right here is equals probability of square root of x smaller than y right here. Or maybe I try to write this way. You guys possibly would have in that clear pictures. So fy right here, based on definition, I have y smaller than y. Okay. Then you ask me about, hey, y equals to square root of x, right? Right here. Okay. Then would equals probability of what? This guy right here. I'm working very hard trying to put x along in the left hand side. So by this means it's x smaller than y squared, isn't it? Right? You're taking square here, taking square here. Okay. Of course, I want to mention one thing is the negative side, the smaller than equal side doesn't change. Why doesn't change? I will leave it to you. Think about it. But later I will mention. Sometimes the direction may need to be changed. Okay, but in this case, you don't have to. Okay, so then you put your all random variable, all random variable right here, smaller than something, right? So again, it's nothing but CDF definition of what? Of all random variable x, right? That means if in terms of CDF notation, I could write it this way, right? All random variable, this guy is only argument, again, little case right here. Okay, then you're trying to find is what? Okay, you told me x follow exponential lambda. From the distribution table, you can actually find what the CDF is of exponential lambda. Okay, so that means actually I can actually memorize it, should be minus x divided by lambda right here. Okay, good. So then if I have in that CDF right in that way, this notation, nothing but plug in my little argument. Why I change to become this, man? right? Right here. So really nothing but this little argument right here goes to what? Goes to where the x is, right? Really nothing but 1 minus exponential. I plug in little y squared, then divided by lambda is. Okay? Then you finish. You derive me a distribution of y. But if I first asking you what's the PDF look like, right? Right here. Nothing but what? Nothing but what happened? So nothing but doing differentiation of the CDF to become PDF. Okay, then doing differential right here should be easy, right? Minus 1 goes away, exponential minus y squared divided by lambda. And then, do I finish? No, you need to do what? Chain rule right here. So chain rule right here become what? Minus 2y then divided by lambda. It's okay. Then you summarize everything, become, I think, become 1, I should say 2y divided by lambda exponential minus y squared divided by lambda. It's okay. Exactly. This is lambda. Exactly. I wrote it right here. Good. So that means that's how you're using CDF to derive the distribution. Oh, sorry. Okay. So then, looking at this PDF, you could actually find from that distribution table, which is y equal to lambda. It's okay. But I think a lot of times it's you won't be able to find the named distribution, to be honest with you. But using PDF right here, you could do a bunch of inference already. Not necessary to be named it, or not necessary to identify what distribution that PDF is. But in other times, if you know that's some PDF, for example, gamma family, then it could give you some hint to see how I'm going to do transformation for the family to become other distribution. Okay, so that means, well, I got my PDF. If I can identify what a PDF is, it might save you something for you to go to the next step. But however, even you don't find it, even it's not common PDF, it's okay. You could still do inference in the future. Good. So then, that's one example. The next example would be this, right? If I have my x normal 0, 1, and then right now it's if y is x squared, right? Y again, transformation, and then x squared. That means if I'm deriving the CDF of a new random variable y, right? Number one, you are choose what? Hey, how about definition? Again, definition right here, right? Definition right here. Okay, so then using definition, if I want deriving y is x squared, right? Definition of y of the CDF, nothing but probability of y smaller than y. Okay, the same thing right here is what probability. I plug in y as x squared, then smaller than y is. Okay, then you do your best, right? X squared smaller than y. That basically told me that it's x is between negative y square root of y to positive square root of y is. Right? That's how we find x domain is. Right? If x squared is smaller than y. Then right here, again, similar to, but not the same thing as exponential case, right? In the previous case, you only have one direction right here. Okay, one direction. Right now you have what? Two inequality. But that's okay. We could live with it. Okay, because this guy is really nothing but what? Right, minus probability of small than minus y right here. Right, in picture wise, it's nothing but I have normality, normal 0, 1, it's right. I have normal 0, 1 right here. I'm asking you to derive in the probability from negative square root of y to square root of y. It's nothing but deriving the area in between its 2 points, right? Of course, you can have what? Bigger area right here, right? Bigger area, then minus small area right here, right? Small area. Okay, easy. And then first equals to what? Based on notation we always use for normal 0, 1, I have capital phi right here. I pronounce it phi. If you strongly say it's pronouncing phi, I'm okay. Okay, so good. This guy nothing say phi minus y. Phi function, you guys know it is phi function means usually in conventionally it's a CDF of normal 0, 1. It's okay, good. So then basically you finish right here, I think. Okay, because you do derive in the CDF of y, but in the phi function. Actually, we really don't know what closed form of phi function is. Okay, or I should say capital phi function is. So we don't really writing down what the CDF of normal 0, 1 is. But if I want deriving the PDF from CDF, again, nothing but doing differentiation. Right? And then right here is what? I do this, let me take out something. If I do this, right? I do this on differentiation. Then capital phi in terms of differentiation become little phi, which is a PDF of normal 0, 1. Okay? Did I finish? Don't note. Right? I did not finish. I did not finish is what? Because I do need to pay attention to this guy is still function of square root of y. I need to do what? Chain rule. Okay? Don't forget about chain rule. And then if this chain rule is applied, okay, let me take out everything. I want to write it more clearly. If I apply chain rule, this guy means what? This guy means 1/2, 1 minus 1 and a half right here. Right? Square root of y is nothing but y with power 1/2. Then you put 1/2 going down, then your power side you minus 1. That's how you do chain rule. That's how you do differentiation. It's okay. Again, I have minus right here. Doing this part again become phi, go to the y, and then minus y. And then you do chain rule. Then be careful. Okay, you need to have minus side right here. Otherwise, everything will screw up. Okay, then you sort of simplify that, become like a phi, go to y, then half y minus half, then plus phi again minus y, then half 1 minus half. Okay, could I even further simplify? The answer is yes. How? The first one is I do a common term right here, then I can pull them together, then become this, right? Okay, that's one way to simplify it. Could I even simplify? The answer also yes. How about these two quantities? What does that mean? That means it's if I have a normal 0, 1, yeah, it's ugly normal 0, 1. Sorry about that. So I having this guy minus square root y, that guy square root y. Where does this little phi square root y is? Nothing but here, right? The whole curve is a PDF of normal 0, 1 is. So of course this guy is what? Phi square root of y. This guy is phi minus the square root of y. What does that told you? That tells me these two guys are equal, right? They're the same height right here. That means eventually I can write that this guy is 2 times phi square root of y up to cancel out, eventually become y minus half, then phi square root of yx. Okay? Do I know what phi x is? I don't want to write y right here if you're confused. What is the PDF of a normal 0, 1? You should know that, right? It's been so many years you guys studying statistics, right? Normal PDF is something that would keep saying that you could memorize easily, or saying that it's in your brain already, right? So 1 over square root 2 pi sigma square is 1 right now, so it's only square root 2 pi. Then minus actually 2 sigma square, right? 2 sigma square is 1. So 2, then x squared is x minus mu, then taking square. Okay, this is what normal 0, 1's PDF is. Then right here, eventually nothing plug in square root of y, right? So I doing this 2 pi exponential minus 2. You put down little guy to where? To this guy right here, right? I have square root of y, taking square, then become what y is. Okay? Then eventually, if you want to be clear, sorry for my really bad handwriting right now. I still need to get used to the writing surface of my iPad. So this gonna become, I would say, minus y divided by 2. That's okay. And then you'll find out this guy is a PDF of what? Of what? Right here. In the first class, I said if x normal 0, 1, if I take an x squared, then become what distribution? Become chi square 1x. Then you will find out this PDF exactly chi square 1's PDF. Okay, good. So although you possibly would know or having read a lot about x normal 0, 1, x squared chi square 1, but this is exactly the derivation you need to learn or you need to know in my class. Okay, so in my class, a lot of things is you know that, but I'm trying to teach you how to mathematically prove it. So far, so good? Any questions? Okay, I will take a note. Okay, let's move forward. So there's a common transformation I want to teach you right here. And then it will be useful and it'll be useful as well in the future in my class. So I want to mention it. So-called inverse probability integrand transformation. Really nothing but using CDF as a function to transform the old random variable to become new random variable. This is one typical case you will see it. Say, suppose that f is continuous. So f is CDF function. I say f is CDF function itself. Suppose some CDF function is continuous. and strictly increasing, right? You see CDF, right? CDF is always from 0 until 1, right? From 0 to 1. That's what domain of CDF is. So in my class, we are not trying to be picky, which means that we are not like a mathematical class. I told you that hey, some function is like discontinuous at some point, and then what's the probability of like a right continuous or left continuous function? No, we don't. Again, we are not mathematicians, so we are going to deal with their complicated cases. Okay, so in this case, it's always like a much more easier setup. I give you continuous function, so you don't have to worry about whether or not it's every point is gosh, I'm tired. So if does every point is differentiable, okay, you don't have to worry about that. And then I always give you so-called monotone function. Monotone function means either it's like increasing or decreasing. Okay, so I'm trying to get your life easier. Good. Okay, so then suppose that I do have original random variable u follow normal 0, 1. Then I can actually give you a new random variable y right here using so-called inverse of CDF as a transformation tool right here. Okay. Again, logic question is I give you some function, right? I give you like right here is nothing but really equals to yg function transform the u random variable, right? So even though I told you f is a CDF, right? It's continuous, strictly increasing. Then I can proposing, hey, can I do transformation now inverse of CDF? You could. Mathematically, you actually could. And then tell me what is the distribution of a new random variable y is, right? Again, fine, definition, right? Let me derive CDF to see if I can succeed. If I fail, then I choose another route, right? So let's try definition. So again, definition, the CDF told me that it's probability y smaller than y, right? So I do record the class, right? Yeah, I think I recorded, hopefully. Good. Okay, then you told me that it's what? The new random variable y is coming from the transformation as inverse from u, so only y. Okay, again, so far so good. I can do it. And then right here, okay, from their previous two examples, to me, it's you're really trying to working hard to put your u in the right hand, even in the left hand side, right? Even though I do know transformation y equals f inverse u, but it looks like you need to try your best to put your random variable, old random variable u or x in the left hand side. In this case, I can easily do it. Why? I can apply the f function again in the left hand side, then I can isolate the u. The reason I say so is this, right? I can apply, oops, I did not go to, right? Okay, so I can apply f function in the left hand side, then become f inverse function right here, right? If you really want to be strict, you want to write right here, but it's fine, right? So something like that. And then you apply f function in the left hand side, you can also apply the f function in the right hand side, become fu. Okay, and then go on is what? F function, f inverse function cancel out, then become u function right here. Okay, and then smaller than fy right here. Okay, and then how do I know what its probability is then? Right? Remember, u is uniform 0, 1. If you put up uniform 01's PDF. Nothing but what? Uniform 01, domain from 0 to 1, okay? PDF as well, this guy nothing but 1x. Okay, this is basically a graph of the uniform 01. And then you're asking me, hey, if I having the constant right here called Fy, and then this guy nothing but calculating the area of this kind of rectangle, it's this rectangle, right? And then what is this then? What is area then? Right? I usually joking that is even my middle school daughter would know what area is right here. Okay, what's area? Nothing but Fy, isn't it? Right? This guy is length, this guy is width, so it's 1, this guy is Fy. So of course it's Fy. Okay? Maybe you are so smart, you look at this, you will know this already. Okay, hopefully you could do that at the end of the semester. I don't have to draw this graph to you to explain to you why area under the area under some point of uniform 01 is the point itself. Okay, good. Then what does that told you? Let me be more specific. I want to do it. I want to do more solid notation. It's I would say this guy is f of still f of y. Yeah, I don't think I can do better right here. So what does this guy actually means then? Okay, even though I finished right here. Okay, so that means this is usually used back into the days when we don't have that much of computing power, but you still want to generate it, some random variable follow some distribution. For example, right here. Okay, say if your target function or you're saying that is if your target distribution is exponential 1 right here. Okay, nowadays you go to R, you plug in R exponential R exp, and that could give you generation of it give you any number of the exponential 1 is. Right? That's easy life. But imagine back into the days when computers not necessary so powerful, then how people get a random numbers or random variables that would actually follow exponential 1, right? Then smart guys look at this and say, yeah, how about I actually generated uniform 01 first? Uniform 01 is easy to generate, isn't it, right? You flip coins, you roll a dice, you open a book, you do anything random, right? And then you squeeze it, become normal 01 is. As long as the domain from 0 to 1, you imagine anything as a randomness, right? You could generate a uniform 01. So uniform 01 is easy number to generate it. Then if I do know F inverse function, then by this derivation, I can basically told you that it's through the F inverse function, I can make my uniform 01 become exponential 1. But the point, what is F inverse function is? Here, this example. So if I do know y is, if a target distribution is exponential 1, then I do know I do know exponential 1's CDF is 1 minus EY, like I showed you right here. Right? Where is that? Right here, right? This is F, this is exponential lambda, so CDF. Okay, so say if I do know F inverse function, right? Based on this derivation right here, that would tell me that I can actually deriving an exponential 1's CDF. Oh, so I'm sorry, I can actually get the random number of exponential 1x, which means that I can generate the u from normal 0, 1, and then do this F inverse transformation, then the CDF y eventually is a CDF of the y. Okay, good. So in plain words would be as long as I can generate the u from normal 0, 1, I'm finding this inverse function of new random variable, then by their mathematical proving or statistical showing, I can show that the new random variable y is going to follow exponential 1. Okay? Then, but point is, I do need to know what f inverse function is. Okay? Then imagine if you really want to use in the same strategy to do that derivation, to do that generation of normal random variable. Again, the whole derivation right here actually told you, as long as you generated uniform 0, 1, as long as you do know F inverse function, then you can get a random number of normal 0, 1x, for example. Okay, but the point is, does F inverse function of normal 0, 1 is easy to derive? The answer is no. I told you in terms of phi function, capital phi function, right? I have told you that we don't have closed form for phi function already, right? Well, letting alone, you don't have closed form of a phi function, and you want me to derive in the inverse of phi function. It's just not possible. Okay, but the tricky part is, I say closed form, which in terms of mathematical notation. Okay, could I using any approximation method to deriving as much close as possible to the phi function or phi inverse function? I think it's possible. Okay, if you do have mathematical background, you should know that it's so-called numerical approximation. Okay, so, but in this class, we don't have to deal with that. That's just an example for you to think about. Great. This guy is about CDF function to deriving the new PDF of a new random variable. Okay. Oh, one thing I do want to mention, sorry about that. Okay, so let me take this out. I'm going to ask you one critical question. Let me take a bunch of red notes right here. I want to see this clearly. When we do derivation, this guy definition easy. You can do it. This guy nothing but plugging. Plugging means you're replacing y as a formation of the transformation would be, right? Also easy, right? You have this guy right here. So just by plugging. Okay. This guy right here, I said apply F function right here, right? The reason I do that is I'm trying to isolate u in the left-hand side because F inverse is going to cancel out. I'm going to ask you one question. Some of you may know, some of you may not, but it's really critical moving forward. Why does this inequality doesn't change? I give you 1 second to think about it. The reason this inequality, yes, thank you. Oh, Weibo, thank you. I'm like a YouTuber, oh my God. The reason this inequality doesn't change is what? This is important property. I basically lay out an assumption is this function is strictly increasing. Strict increasing means bigger value remain bigger value, bigger value remain bigger value, smaller value remain smaller value, bigger value remain bigger value. Okay, so-called strictly increasing. So this guy doesn't change. What if I do give you a function I told you it's strictly decreasing then. If some function is strictly decreasing, then what? Bigger value becomes smaller value becomes bigger value. Then at that time, you need to change your size right here. Okay? So think about it. You would need that in the future derivation, because when we're working on the constant interval, when we're working on the hypothesis testing, you will see at some point you need to switch your direction of inequality. Good. Okay, that's what I'm trying to talk about. Again, right here, I think I'm using the same idea. Good. So I finished teaching about CDF. Then I said another skill you can survive is what? Learning about so-called Jacobian. Okay, Jacobian. Remember that in your calculus class from your freshman year, maybe? Okay, nothing but first derivative of some function we call Jacobian. Okay, good. So let me talking about something much easier. When the function is monotone increasing, right? This guy right here is the same thing as this monotone increasing is the same thing as strictly increasing. Okay. If I function as a monotone increasing, and then if easy life would be 1-to-1 transformation, okay, and onto from X to Y, okay, onto right here, if you don't get it, it's fine. It's not necessarily important to you to understand how these things. But if you have your math in mind, right, you sort of want to say what's onto means. Okay, good. So then, because I doing so-called monotone increasing and the 1-to-1 and onto, so inverse function is actually well defined, and then monotone increasing function as well. Okay, good. So when I am a math major in undergraduate, I really don't like something called well defined. Yeah, it's a long story. That we show it. Well defined is really something I cannot imagine. What do you mean by well defined? Okay, but in this class, we are a statistical class. It's not really that critical to understand what do you mean by well defined. Okay, by any means, well defined means that it's there's no special case. Everything is good. Okay, in our plain words would be that way. And then so that means you can derive inverse function like this way, right? If I have y equals gx, then I can just write x equals g inverse y without thinking about what g function is. That's it. It's so-called g inverse will define monotone increasing function. Good. Okay. The reason I need that also is, okay, actually Jacobian master also coming from CDF master, just give it easier life, deriving a PDF directly. Okay, but based on definition of CDF is y squaring y, and I can, again, this guy nothing but plug in, right? I apply G inverse function in both ends. And then because G inverse function also monotone increasing, so again, this guy doesn't change, right? Because monotone increasing. I apply G inverse function in the left-hand side, I apply G inverse function in the right-hand side. Okay, and then right here is really nothing but definition, right? So G inverse function equals to y, right? Okay, and then it looks the same as with the deriving CDF. We try our best to put your random variable, put your all random variable in the left-hand side. Then if I can create something like smaller than, which means what? Which means the whole thing is nothing but, again, the CDF. Okay, so it means I can have in my y right here, right? Let me write in the right-hand side, maybe just easier for everyone to follow my. Okay, so going up, put here. Okay, again, this based on CDF. This based on inverse function apply both ends, because G inverse function also monotone increasing. Okay, and then this guy is nothing but new random variable y right here. Okay, by definition, right, this guy become x. So then this guy but nothing applying definition of CDF of x. Okay, then this guy is CDF of y. The Jacobian method eventually just directly applying directly give you no, direct give you the new PDF of y. Okay, again, I have my CDF expressed in this way, then deriving the PDF, nothing but taking that differentiation directive. Then again, it's really what? Applying directive on that CDF of x, then CDF become PDF. And then inside guy keep the same. Did I finish? No, right? You see my doing, you see what I'm doing before it's this guy is not only function of y, this guy is not only y, it's a function of y. If inside guy is function of y, what would you do? Nothing but doing what? Chain rule. This is a chain rule you need to do. And then make sure that absolute value right here to keep your PDF positive. Okay? And then this guy right here is nothing but called Jacobian. Good. Then Jacobian method is nothing but doing this. Okay? I find inverse function, plug in to the OPDF. Then I having the inverse function right here, then doing that first derivative to get a Jacobian. Okay? That gives you the new PDF. That gives you a PDF of new random variable. Sounds good? Okay. So right here, I would say that if G function is monotone increasing, then you don't have to put absolute value right here because you will see that as doing that differentiation still positive. Okay. But if G is monotone decreasing, you do need to put minus term right here. Okay, good. So the reason for that is actually not hard to see. For example, it's why does that minus term coming from then, right? So if you really get an idea about why do you need to change the sign right here, right? Let me see. Okay, good. Hold on. Yeah, exactly. So right here, your CDF right here equals applying G function on both ends, right? If your G function is monotone decreasing, your G inverse function monotone decreasing as well. Right here, like I said previously, if your monotone decreasing, larger becomes smaller, smaller becomes larger, then right here, you do need to change the sign of the inequality is from smaller to become bigger. Okay, so if you do that, then because it's bigger, even though I can write it here, say, well, it's x, then bigger than G inverse function of y, right? Then because it's bigger, it's not a CDF anymore, but good news is it's 1 much smaller, isn't it? Right, then this guy is what I used to as a CDF. So that means I can write 1 minus f of then G inverse function is. Okay, so then when you do that, finding that new random variable y, you do differentiation, this guy becomes 0, there's a minus 10 coming out. That's exactly where that minus 10 coming from. It's inverse G inverse y, and then again, nothing but Jacobian, right? Sounds good? Okay, so this minus term is coming out from here. So at the end of the day, as long as you put absolute value in Jacobian, this guy automatically cancel out, become positive. Good. That's the reason why when you're working on the Jacobian method, right here, okay, the formal term will be this. The new PD of y is O PD of x, plug the inverse function, then derive Jacobian, then don't forget about absolute value. Regardless, G inverse function or G increasing or decreasing. Okay? But you always will find it as long as the G inverse function is decreasing or G function is decreasing, then your first derivative is going to become negative. But after you apply absolute value, everything becomes positive. Okay? So don't give me anything about negative PDF, please. It's a common sense in statistics. Okay, good. Okay, I basically finished everything right here. Okay, this is something right, be continuous. Okay, right here. Be continuous, so you have that differentiation. Okay, but you could check a theory right here of Katzenberger. Okay, let's look example, possibly much easier for everyone to look at what happens, right? Let me point right here. Bigger one, can I give one? Oh, that's too small. Okay, so right, good. So I say example is, again, exponential lambda. Well, you might see that before in CDF methods. Then how do I do that in the Jacobian method, right? I have x follow exponential lambda. Then I'm trying to deriving y equals to square root of x. That's right here. It's easier for me to do derivation. Okay, using Jacobian method. Okay, nothing but hey, I can derive in the PDF directly, and then put it down as what? OPDF. And then inside guy is so-called inverse function. Inverse function right here, nothing means I do put x in the left hand side, then become y squared x. Right? Okay. So I'm just got right here, this guy inverse function, this guy inverse function as well, then plug in y squared x. So again, I do know inverse function is complicated, but in easy term, inverse function would be this guy original function, left hand side is y, this guy inverse function, left hand side is x. Okay, that's easy approach to imagine what inverse function is. Okay, inside guy plug inverse function, then deriving Jacobian. This guy, sorry, this guy is inverse function. I totally wrong in notation. I'm trying to take it out. It's not a good term to do it. Okay. This guy right here is d inverse function y squared, then dy is what I'm looking for. Okay. Good. And then the rest of work is nothing but plug in. Of course, I need to know what the exponential lambda would be. So this is something I want to talk about. In my class, the standard exponential distribution I always use as a PDF is this way: 1 over lambda exponential x divided by lambda. Okay, Some of you might say, well, what I learned is lambda exponential lambda x. Well, it's okay. It's the same thing. It's nothing but the so-called using new parameters to define it, the new PDF. Okay, so, but in my class, I always, when I say if I forget to mention a PDF, it's this way, then you always having that in mind, unless I make it specifically saying the exponential lambda is lambda exponential minus lambda x. Okay. So that means, okay, this is my PDF of exponential lambda. Then nothing but really plug in then, right? This notation means I need to plug in where the y square is into lambda. I need to plug in y square into where lambda x. And then this guy right here is to the right, nothing but 2y. Okay, so then I think you finish, and then you don't have further thing you could work on. Eventually, it's 2y lambda exponential minus y squared divided by lambda. Okay, of course, right here, maybe in 661, maybe in 660, you will learn it because exponential do having that, oh no, exponential as a positive, of course, y in terms of domain, taking square root of x, then y also positive. And then possibly the professor told you that it's keep your habits, writing something outside a domain, PDF is 0. I'm okay with that. Okay. So in my class, you don't have to be that strict because I do not understand. But again, I say the first class, this is good habits, right? After writing down PDF, you write where the domain is. You even write where the parameter space is to make sure that you get it. Okay, so in Jacobian, we talk about G function is monotone. What if the G function is not monotone then? Okay, so for example, right here, okay, so you would gx function right here, say you do this transformation right here, right? You have x, you have gx right here, right? You do x squared, say if x from minus infinity to infinity, okay? If you do x squared, you basically is this guy, right? That's x squared function, right? And then you do have what? One part is monotone, one part, I'm saying, one part is monotone increasing, this part monotone increasing, this part monotone decreasing, right? So we talk about Jacobian method. If you have either monotone increasing, you need to having some positive, monotone decreasing, you need to have some negative. Okay, so if you do that, then how do I working on something as a G function transformation is not monotone? Easy. You just take that. You just break down your domain into participation, which means that I can talk about something for this domain x bigger than 0, monotone increasing, I follow some rule, and then monotone decreasing, I follow another rule. Okay, so this guy is really nothing but, hey, if you want to talk about using Jacobian and Jacobian working like a monotone increasing function, oh, I'm sorry, Jacobian working on monotone function directly, then if this is some, if it's a function give me some part of domain is monotone decreasing, some part of domain is monotone decreasing, how I do it? Nothing but just break down in partition. Then in each partition, you're working on the same way as Jacobian should be. Good news is, how do I combine together? Nothing but just sum them together. Easy life. Okay? Good, right here. Okay, 10 minutes to go. Hang in there. Okay, so then again, I have x normal 0, 1, right? Right now, my transformation is y equals x squared. By doing so, using CDF, I will show you what the result is. But let me do using Jacobian. Okay, again, like I see right here, I said because y transform from x normal 0, 1, domain is minus infinity to positive infinity. And then the transformation would be it's right, monotone increasing, monotone decreasing. There are two parts. But again, I can always put 0 right here to infinity as a so-called A1, I think. A1 means the first partition. Then A2 right here become second partition. And then A1's function monotone increasing, so I can use Jacobian, one Jacobian. And A2 is monotone decreasing, so I can use another Jacobian. Okay, so I can derive into Jacobian separately. Okay, so let's do it then, right? So I do have like, if I talking about something here, if x belongs to either way put 0 to infinity, right? It's A1 means maybe I can give this 0 to A1. I don't give 0 to A2 then. There's a better mathematical notation. It's okay. So then, but you will find out it's both are the same thing. So say if I do need to deriving the new PDF of y, again, I'm using OPDF right here, right? So y equals to x squared. So y in the left-hand side, inverse function is x in the left-hand side, okay? Because x is positive, so I can put square root of y right here, right? As a transformation, okay? But if x is actually negative, your transformation is minus y as inverse function. Making sense? Okay, so really depending on the domain, the transformation are different. In the inverse function are different. Okay, so I'm working on A1. This is A1 domain. So this guy become plug-in the inverse function. And then doing that Jacobian derivation, of course, I always put something as a absolute value. That would much easier. Okay, so x would be normal 0, 1. So I just write directly exponential minus 2 sigma squared. Sigma squared is 1. So I actually don't have to put there in. And then 2 sigma squared is what I have. And then this guy is x squared. X squared plugging square root of y become x squared right here. And then you're working on the Jacobian. This guy right here is 1 over 2, 1 minus half x. Okay, good. And then if you're working on that Jacobian right here in the left-hand side, right, if A2 based on domain of this guy right here, A2. Okay, so inverse function become negative square root of y, right? And then again, you put a Jacobian right here, and then dy, just by any means, everything is just put absolute value. I think it will be fine. Okay, you plug in, then again, it's this guy right here. You will find out it's even you have minus square root right here. After taking square, they are basically the same. Then I can write right here. Okay, good. So that means either A1 or A2 as a two partition, the PDF of y turns out to be the same. Then I teach you saying it's okay, if you do partition, you're deriving the two PDF and different domain of x, then eventually good news is how do I combine it together? Nothing but sum them that are the same, nothing but identical. So I can just times 2 then. Okay, Again, this PDF is chi-square-1's PDF. The same thing as using CDF methods to the transformation of x normal 0, 1, then y equals x squared. Okay, one last bullet right here. Hey, thinking about why Jacobian does not apply to discrete random variable. Why? You don't have differentiation on the discrete random variable. That's it. So you don't know what a Jacobian look like. You cannot define it. That's the so-called will define. Okay, good. So 4 minutes to go. I have to told you that you are going to have homework number 1. I kind of will post it in the evening and will be due next week. Please don't complain. Only 2 classes so far, and then you got homework. Yes. But in the meantime, don't worry, you won't get tough one. Okay, I will just give you a bunch of transformation. You work on it. Okay, and then it could be possible I give you more Cassandra questions. So you having something online you could look at. If you really struggle, then go to solution menu and then to see if you get it. Again, don't copy the solution menu. That's all I can say. Okay, because if you copy it, we all know it. Good. So again, everybody understanding math different ways. I bet you have your own way to understanding what I'm writing right now. Okay, so do it and then practice a little bit about how to do transformation. Okay, let me quickly saying something about bivariate and the multivariate transformation in a much more easy way. Okay, so again, using for discrete random variable bivariate transform discrete random variable, even it's bivariate, it's still nothing but enumeration, nothing but counting. Okay, again, x, for example, bivariate, x Poisson lambda 1, y Poisson lambda 2. If x and y dependent, cannot deriving u as x plus y. Okay, anyone could tell me what would you follows without any derivation of the Poisson PDF? I think you got to know it if you want to get a degree. Okay. X plus y, x1 dependent, Poisson plus Poisson, nothing but still Poisson, easy. But your parameters as a real value of the Poisson is lambda 1 plus lambda 2, also easy. Okay. But right here, if you want to do that, again, nothing but counting. This is straightforward to us right now. But if you want to know about what happens, then nothing but this. Okay, your u is x plus y equals 3. How did you get x? How do you get u as 3? Nothing but counting by how many x and how many y to give me u as 3, right? We all have the college degree, so it shouldn't be a problem, right? X and y, 0, 3, 1, 2, 2, 1, 2, 3, 3, 0. Will give me u is 3. If you're doing that way, then you're basically working on each probability. Then the same thing as we did when we do univariate, right? X and this guy join PDF because X, Y independent. So I can write probability of individual times individual. Okay. Then by doing that, you just calculating X is 3, then having that Poisson PDF. X for factorial lambda 1 right now, then e minus lambda 1. That's what probability of x is. Then another one is Poisson. Sorry, y exponential lambda 2 e minus lambda 2. Okay, then you just plug in, you just using it to PDF to calculate the Poisson PDF. Okay, 45 right now. I don't want to bother you further. So any questions? We can stop here. Although I do wanna talk about primary Jacobian, but I cannot going further. So, oops, you see bunch of my scheduling. I should close out. I'll do it next time. Okay, any questions? If not, you may go, and I will see you on Monday actually. So I'm going to post it and easy questions about transformation this evening, and we will talk about that next Monday at 12:15. If you feel like you wanna knowing further about how to do transformation, okay, but I think it should be straightforward. Okay, so anything else? If not, I'm going to close out the room. I will see you on Monday, but email me whenever you have anything in mind you want to talk to me. Bye-bye.